Today I'm going to talk about the work we have done in SmaDi. A specific point, namely therein, called the point of integrity constraints. And I will talk in the end a little bit about bridging axioms. So let me start with this small cartoon. I think most of you know about the Mobius strip, which does not have an orientation. And so this motivated actually this cartoon that Mobius had the trouble that he thinks there's only one side to every question. And actually, the point I want to make here is that in doing a form of ontological engineering, it's not really only about modeling ontologies, but a little bit more. And this will be the main content of today's talk. So you heard it already, SmaDi is about the digitalization of smart materials and the manufacturing processes. Well, we have had various demonstrations of what has happened there. Today there will be no demonstration, but I will talk about, as said before, an additional component, namely SHACL constraints, and why we need them actually. Before that, let me remind you of what we're doing in SmaDi regarding the information processing paradigm. Namely, it's ontology-based data access in the classical sense. So the main architecture is this. We have information users with information needs, and the main point here is that the information is stored in relational databases. And we want to access them via an ontology. And usually in the narrow sense, an ontology is called, at least in the description logic community, a terminological box. So here we have, if you want, terminology described by definitions. And the database information is stored as a logical view, sometimes also called the A box. And this is done via mappings. Yeah. And the main point of accessing the data is now that we're not using some deductive reasoner, but we're using a form of query transformation. So we have a query, say a SPARQL query, which is then extended, first of all, with respect to the terminology. So it gets pimped up in order to account for the possible implications of the T box. Yeah. And then this extended query is unfolded with respect to the mappings. So a query using terminology from the T box, is transformed to an SQL query, which is answered over the database. Yeah. And OBDA does something very special here. I think most of you know this fresco of Raphael in the Vatican, showing the School of Athens. Oh, there's someone. I heard noise. So we have the School of Athens here, and Plato there is showing upwards to the area of ideas, and Aristotle is showing downwards actually. And so the viewpoint I want to make with respect to ontology-based data access is that the ontologies just live in this world, and databases where the real data is. This is the our it's not heaven. It's the concrete world with all the mud and so on. Well, the main point is that ontologies adhere to the open world assumption, whereas databases don't. Yeah, and this point will be raised again in this talk here, and this the reason why I mention it here. What OBDA does is taking the database level, lifting it to the ontologies via the mappings. In a concrete case, these mappings are R2R ML mappings. Yeah. And in order this really to work out, we have to restrict our ontology language. Yeah. So, and this has consequences for how to use our system um, together with the PMD core ontology, say. So we cannot use the whole OL2 fragment, but we have to use a smaller fragment so that query transformation really works out. Yeah. And this is the reason why I wrote up the ontologies in this small font. Okay, and this motivated us now to the question, should we really follow OBDA or can we do something else? And this led to the model of ontology-based data access to data and models, where now the guiding idea is that it is not really about just modeling the ontology in the stricter sense, the terminology, but anything here which we have, namely mappings, the queries, and so on. These are also artifacts which we want to model and which we want to exploit in a very a strong sense. Yeah. And so actually material models from material sciences, they reside here somewhere in the whole system distributed over all the artifacts. And I will demonstrate what I mean by this. Yeah. And it begins with accepting that you have various places on which you have to model. And using this idea, you can think of somehow redistributing knowledge in some level to other levels. Yeah. Now, why is this useful? Well, because we won't be able to express everything which can, for example, be expressed in PMD core in the terminological box here, because we have to rely on a fragment of all two, namely all 2PL. So the idea will be actually to move some aspects to other artifacts. Before coming to this point, let me mention that in SmaDi we have different, actually four smart materials which we work with, and the models in the first phase of the project, at least, were just specific functions, yeah, relating some say forces or whatever with other kind of variables, yeah. And actually, these kinds of models then were really mainly implemented in the database. Yeah, so we really took care of functions by, well, putting them into the database and using them there. Yeah. One could also think about, yeah, somehow describing functions, those models also on the A box level, but also about trying to constrain what we expect from functions in the terminology. This is rather, and this is the reason why I have put it into brackets. This is work, outlook for future work, because it's not trivial and to implement functions on that level without losing the ability to transform queries. Yeah. What we have done is really to have functions, some form appearing in the query language. So we talk there about conditional queries, which should remind us of conditional probabilities. Yeah. And then we developed various modelings and queries on the different use cases, following the idea of letting our colleagues write up all the models in Markdown document and then yeah, formalizing this in OL, 2QL, and the corresponding queries there. Yeah, and so it is possible then to write up queries which formalize something like output a new Hookean Y module for active elastomers, or asking to do a parameter fitting. Yeah. Okay. So this was the reminder of the OBDMA approach, and here's the main point for today, namely that the main ontological artifact, which we are going to consider next to ontologies, are integrity constraints. I suppose that most of you know about integrity constraints from the domain of databases, yeah? So foreign key constraints and so on. And something similar is desirable to have directly on the A box level, yeah? So we have an ontological vocabulary, and we have a logical view of the database, which we call the A box, and we want there to formulate some integrity constraints. And let me state it from the beginning, in contrast to ontological axioms, these integrity constraints are meant to capture data patterns. They are somehow less intentional, as they do not talk about any objects, but just objects which you have in your concrete A box. I will illustrate this with an example. And somehow what we gain there with is an additional expressivity, which is orthogonal to the expressivity of the ontology language. Okay. So keep this in mind. And now here's an example of what I would call distributive modeling with ontological artifacts. We had this somehow innocent looking definition of a DE transducer, which says a DE transducer system consists of many transducer foils that are attached onto each other. Yeah, so this is from a markdown document. Well, it can be stated, easily stated in natural language, but our natural language is quite flexible. So first of all, what comes into mind is to express this in a very expressive logic, like first order logic. Yeah, but actually one can show that this is not easily expressible in first order logic. I would say it is actually not expressible, and forget about expressing it in all. Here's the argument. First of all, yeah, this seems rather marginal point, the point of many, which hints to a so-called generalist quantifier. Yeah, but even if many would be translated at least two transducer foils, yeah, it would not be representable, because the main problem lies within the structure you have of transducer foils being attached onto each other. So what you have here is a linear graph. So this query requires identifying the linearity of graphs, yeah, and actually one can show with tools of so-called finite model theory that you cannot identify a linear graph within arbitrary graphs. Yeah, this is a query which is non-local, and first order logic queries all are local, so cannot. So this means this query cannot actually be expressed in first order logic. Now, the point is that it's a linear graph, and you do not know about the length of the graph. If you would know about the length of the graph, yeah, the number of transducer foils, and say, okay, I can bound it from above. Say it must be maximally m transducer foils. Then, of course, you can express this. Yeah. Yeah, because then you do not have to think about the number of foils, but you can say it's just that number of foils up to m. And then you can formulate first order logic query. The details do not matter here. I just wanted to show you it is possible then. But still, you cannot formulate this in all, yeah, all two, because, and here comes the other point, you have actually a structure. Yeah, you say you have a DE system, which is a linear graph. Yeah, and this means that you actually have then a cycle. Yeah, starting from the object DE transducer. And yeah, and this means actually all which is based on the description logic, which has the tree model property that you cannot capture such kind of structures actually. Yeah. What would one do then in such a case? So assume you want to express it in an T box with all two. Yeah, the standard solution would be then to do a form of approximation. I will show you in a second how this could work out. And then I will argue that we rather would go for a different approach, namely the distributed approach of doing approximation by pushing this knowledge artifact into less intentional level artifacts. So by approximation, what I mean is that, in this case, we would get rid of the attached to relation. Yeah. So I use here the description logic terminology, which says a DE transducer is equivalent to something which has a part some transducer foil. Full stop. Yeah. So you completely forget about the structure according to which we required, yeah, the being attached on. But then, of course, you lose structure. Yeah? You do a form of approximation. This still would not be an O2QL, which does not allow to have so-called qualified existentials, yeah, where you say you have a part and this part has to be of a specific form. This is not allowed on the left-hand side. And so what you would do then is, or could do, is get rid of this qualified existential and introduce a specific role called here part with an index trans. So this is possible. And before I come to our solution, let me mention, well, this was easy, yeah, for the single sentence, but how would you do it systematically? In particular, if you have a full T-box, set of T-box axioms, which may entail additional facts, yeah, implicit entailments. Uh, um, and there's this general idea of approximation, where you have given an ontology or terminological box in some rich logic. Think of first order logic, yeah, and then you want to produce an ontology in a weaker logic, yeah. First order logic, you want to have an ontology in all, say, yeah, and then what would be a good criterion for having an adequate approximation? Well, your approximation should deviate only minimally from the original ontology. What does this mean, deriving minimally? So this can be done by referring to the notion of an entailment set. So you look at any kind of sentence of the weaker language, which is entailed by the ontology in the richer language. And then you want your ontology to capture most of this. Yeah. Unfortunately, this does not mean that you would then generate a unique approximation. Actually, it could be the case that you have approximations which are equally good with respect to this deviation minimally. And so you would actually get many approximations. And well, calculating this approximation is not really feasible. You can do it, so the algorithm could be brute force, but you would have to check quite a lot of potential approximations. Yeah. Okay, so then this is not the way we want to go. In the distributed approach, we want to model this knowledge artifact on other levels of ontological artifacts. Yeah, and for today we're gonna have a look at integrity constraints as some form of less intentional ontological artifact. And we specifically here look at SHACL, which is also a recommendation by the W3 consortium. So here are some words on SHACL. And here comes the fresco again. Again, ontologies adhere to the open world, database to the closed world. The T-box axioms are those which, these are the first class sit-ins on the ontology level. On database, we have database integrity constraints, and the SHACL integrity constraints. These live on the, if you want, the level directly over the database, on the A-box level. Okay. Here's an example. Assume that we have this knowledge artifact. Every specimen has an associated material. quite simple an artifact, and as a T-box axiom, quite easy to set up. Yeah, here again using the description logic notation, the class specimen is a subclass of this class where you have an associated, where you have a qualified existential telling us this is the sorry, the class of all things which have an associated material. Yeah. So now this T-box axiom has to be read in the following sense. It says, no matter what the situation is, no matter what the state of affairs is, for every specimen, it must be the case that it has an associated material. Yeah. And meaning, so talking about for any situation means for any a world. And this is the reason why we talk about the open world assumption. Yeah. On the other hand, as an integrity constraint in SHACL, it would have this form. It does not really matter how the syntax is working. Well, actually, this is by in SHACL, it works with two different forms of constraints. One's where you specify constraints directly for a node. And in this case, we given a constraint for the class specimen, and we talk about what about constraints which must hold for properties of the specimen, yeah, which says here that if you consider the path along the association role, then you must ensure that there must be at least some element which is of the class material. Okay. In the end, it sounds quite similar to what has been expressed in the T-box axiom. But as an integrity constraint, this is meant to hold just on the actual A box which you have. Yeah. So what you assume here is a closed world. You do not think about other possibilities here, but just the A box which is given there. Okay, so I'm talking about just the A box. So then let's make up an A box here. So I need a little bit more space, and here's the A box. Where is it? There. Yeah. So assume this A box, which says I have some specimen, a specimen S1, and for this specimen I have mentioned an associated material EL. Yeah. Furthermore, in my A box, I have another specimen, S2. But for this one, I did not mention any associated material. Now, the main point is the T-box axiom is consistent with this material. Because we have with the T-box axiom the assumption of open-worldedness, what the T-box axiom is doing is actually completing the A box. Yeah. Yeah. So it says, well, in any world, it must be the case that any specimen must have an associated material, and so must S2, though you do not have mentioned it. Yeah. But not having mentioned something in your A box doesn't mean that it could not hold. This is the idea of the open worldness. And because of this, you get this seemingly paradoxical situation. So if you have a query which asks here, the first query Q1, it asks for things X which have an associated material. If you just look into the A box, yeah, then you would say, yeah, S1 has this fulfills this pattern, so it must be in the answer set. But the specimen S2 does not fulfill the specimen. But we know, well, that if you want to look for things which have associated materials, you could also, according to the T-box, look for specimens. And indeed, S2 is specified as specimen. Yeah. And so according to the so-called certain answer semantics, also S2 fulfills this pattern, yeah, and must be in the answer set. If, on the other hand, you would also ask for things X with concretely naming the material, then in this situation, you could only name S1. because only for S1 the concrete material is named, whereas for S2 is not. Yeah. In contrast, the integrity constraint, yeah, is not valid here. Yeah, because the integrity constraint says in your concrete A box, you must ensure that for a specimen, you have to have an associated material there. Yeah. And so the integrity constraint would check really for completeness and would see, no, the constraint here is not validated. Okay, so I motivated using integrity constraints by yeah, by the constraints of our OBDA system. Yeah, we cannot express as much as we would like to, as in PMD core, for example, in our T-box ontology. So we have to do something else. But nonetheless, I think also in those cases where your T-box is quite expressive, you sometimes need to refer to integrity constraints because these are somehow dual, yeah. Because here you're talking about the completeness of your A box, yeah. So independently of whether you using OBDA or whatever, it would be good to have integrity constraints, yeah. And in particular, this is the case if your knowledge artifact is something very specific about your A box, not which you would describe as being true under any circumstance, terminologically true. This is the example I like always to mention. You know that the mammals are just the animals which have an earlobe, yeah. But of course, you would not define mammals as being something with an earlobe. Yeah, I hope you get the point. This is then rather something expressing what is the case in the actual world, but not something which you would say as defining mammals. Yeah. Okay, and so what we did is yeah, next to having this idea of distributing knowledge artifacts onto different artifacts is really setting up a SHACL validator. And the main driving idea in setting up the SHACL validator was to consider SHACL constraints actually as SPARQL queries, yeah, which monitor your system. Yeah. As said before, SHACL is a recommended W3C standard. And with this, of course, you can expect that there are already SHACL validators available. So why did we write a new one? The new one actually uses the idea I mentioned above, that SHACL constraints can be considered as some other syntactic form of setting up SPARQL queries, which are monitored. And actually, we translate one SHACL into possibly many SPARQL queries. And why did we do so? Because the available SHACL validators, they require an A box being available. As you remember, our A box is not really constructed in the OBDA approach, but it is a view. Yeah, so it's virtual. Remember, query answering works by transformation. We do not materialize an RDF graph. Yeah, so we couldn't have used actually a standard SHACL validator. That's the reason why we built a new one. And here's an example what you can do actually. So this is given in German. Die Blockierkraft sollte zum Beispiel immer entweder mit der anliegenden elektrischen Spannung oder dem elektrischen Feld hinterlegt sein. Ansonsten ist der Wert nicht aussagekräftig. This would not be possible. It would not be possible to represent this as a T-box axiom anyhow. And we could discuss whether this is really an integrity constraint or not. Actually, it is we implement it as an integrity constraint, um, leading to this SHACL constraint here on the right side, which I'm not going to discuss in detail. You might notice that there are some operators here, logical operators there, and this is due to the fact that we have some form of normalization of the constraint of the SHACL constraints in order to set up our SHACL validator. In the last phase of SmaDi, we're now dealing with with some process change for smart materials. Here's an example for shape memory alloys. I'm also not going to talk about this in detail. We have set up an ontology here also for this case, and what we can do here is query on process and the parameters exploiting mappings, of course, and in particular the mappings we have there, and they can actually specify what kind of parameters are not changed. So it is possible then to determine object properties in each of these steps here. Yeah, and here's a very simple example of a constraint relevant here. Namely, fold processes can only be carried out using an elastomer material. Yeah. Expressed here in a very simple form. This kind of integrity constraint could also have been actually expressed as an T-box axiom. Yeah. Okay. Actually, the SHACL validator implements all the properties which are required from a SHACL validator, except for implementing recursive shapes, where you would have the possibility to refer in a constraint to an already set up constraint, which again refers to the one before. Yeah. Okay, so now it's the last point, and then I'm done, and then we can discuss some of your questions. How can we use OBDMI actually within the whole joint venture project material digital? Here are some answers which I want to give. First answer, you could say, well, I want to use the PMD core ontology together with this SmaDi system. Yeah. So, dear SmaDi guys, forget about your ontology. I want to use the ontology of PMD core. Well, as you might have guessed, this is not possible. PMD core uses full OL2. Actually, it uses some constructs which are not expressible in OL2QL. What we could do is to construct an OL2QL version of PMD core. And this is something which you can find also in the literature or out there in the world. If you have an ontology, usually you also provide approximations of it for use in specific profiles of OL2. And one of the profiles is just the OL2QL. Yeah. You could use a simple syntactic approximation if you do not want to refer to a difficult algorithm. You could go through all the axioms one by one and then decide, is it an OL2QL or is it not? If it is an OL2QL, you keep it, otherwise you throw it out. And then you would get a very simple approximation. So this is not a problem. Of course, in order to use the SmaDi system, you would also have to define the mappings, yeah, uh, for your new vocabulary which you might have. Of course, the problem is that you have to care about a good approximation. If you're fine with a simple syntactic approximation, then you're done. Otherwise, well, you have to really implement a good approximation mechanism. Yeah. Answer two would be to say, oh no, I want to stick to the ontology you, SmaDi guys, worked out, but I want to use the vocabulary of PMD core, yeah, in order to get the semantic interoperability. So what you would do then is to forget completely about the axioms of PMD core. Yeah, just keep those axioms which tell you, okay, this is a class, this is a role. Yeah, you keep just the core, the vocabulary of a PMD core. Let's call it V here. Yeah. And then the idea would be that the SmaDi can import the vocabulary of the PMD core. And then you have to relate those different vocabularies. What could you do? Well, you could implement what can be called bridging axioms, namely subclass assertions, subclass axioms, telling you A prime is n A, where A is from the PMD core ontology, and A prime is from the SmaDi ontology. Yeah, of course. Yeah, and now this is the interesting point. This would be done if you think it's appropriate to say, well, what you're talking about in SmaDi is really a subclass of what we are talking about in PMD core. Yeah. This is a simple solution, but the semantics, if you want, is outsourced to the documentation outside the ontology. Yeah. You guys and we guys here, so from PMD core, and we have to discuss about the intended semantics. So there is not a really founded formal mechanism to decide are they simple or how they are related. So there's no real alignment on the ontology level. And this brings me to the last scenario, which I would call the ultimate scenario. You want to produce some added value by integrating two ontologies. Yeah. And the solution then would really use bridging axioms as a simple approach for alignment. And the problem you have to tackle is then which bridging axioms to add. Yeah, and what kind of bridging axioms really do you allow? Are they of this simple form I mentioned before? Do you allow more expressive bridging axioms? Yeah. And as you might guess, and this is the reason why I also called the ultimate scenario, is this is non-trivial. Yeah. First of all, if you want to integrate into ontologies, you have to ensure the consistency of the resulting ontology. Yeah. You want. It could be the case that indeed we may produce inter ontological inconsistencies. You can check for the consistency. There's no problem. There are tools for this. But what kind of bridging axioms then do you really add or eliminate in order to preserve consistency? Yeah. And furthermore, if you want to do the integration and use bridging axioms, then you have better use bridging axioms which ensure that if you add them to the PMD core ontology, what you then get are axioms which are expressible in OL2QL. This is quite a new research question, I would say, which has so far not been dealt with. And we did not in the project now, but this would be something for future work. How to set up bridging axioms which you can add to an ontology in a high level logic in order to ensure that you only preserve axioms which are adhere to the grammar of the lower level logic. Yeah. Okay, so that's it. And in the end, I do not really have a full conclusion, but a take-home message. It is not about modeling ontologies only, as you might have guessed. It's also about modeling various artifacts, also in material digital, I would say. And in this case, it is also about modeling SHACL integrity constraints. And so that's it. Thanks for your attention.